Thank you very much. Right, what I want to talk about is basically what the theoretical possibilities are of making a sort of a space-time reconstruction problem. Suppose you had a compact object and you watch the gravitational radiation that comes from a small inspiraling object. What could you say about the compact object in the interior? So at the moment we basically have waveforms for Kerr Schwarzschild, which I'll go into later. But the calculation requires a certain knowledge of your background geodesic structure and basically how your probe sort of moves in the structure. What we basically want to ascertain is what is the maximum amount of information you can get out by just watching the gravitational radiation, and how would you go about quantifying this theoretically? Okay, so as I mentioned earlier, the no-hair theorems are the reason the reason the current data analysis approach selects Kerr and Schwarzschild as their main central body. They're basically the statement that we make two assumptions about the spacetimes we consider. We basically assume Penrose's conjecture of cosmic censorship, that there are no naked singularities in your spacetime. And the second method of selecting these spacetimes is an assumption we make based on our knowledge of measurement and sort of a bias we have that causality must hold. If you do this, then you select the spacetime Kerr, and it has a feature in it that makes the data analysis of this Emery inspiral problem at this point basically has a feature that you have a full set of isolating integrals. The main thrust of the rest of the talk is finding out how that generalizes, or sort of cataloging what we know of the generalization of this. Let's just have a look at our current Emery sort of waveform generation machine. We have our probe particle moving around the black hole basically in the strong field region. We know it's geodesic sort of motion. We plug this into the Jacoby equation, which basically translates its motion into waves that we see asymptotically and provides the link between the strong field region and what we observe by LIGO. And eventually we get a waveform out, and which we then search for in our data, and we try and ascertain whether it's there or not. And if we do detect it, we go back and we interpret our waveform in terms of our original analysis, and we say, fine, we have a particle of Kerr. It's characterized by a certain number of constants, and it determines the spin and the mass of the central object. So suppose now, in each of these sort of steps of our sort of waveform generation machine, I want to have a look at what the full set of isolating integrals implies. So to get the terminology right that I'm going to be using later on, a full set of isolating integrals basically means you have four numbers that uniquely identify your orbit. These are known as the action variables, and they basically say, given these four numbers, which correspond to the domain or the region in which the orbit moves, basically another way of thinking about them is that they give the maximum minimum radii at which the orbit starts, the angular sort of range that it is spanned by the orbit, and in the two directions of theta and phi. So those are the action variables. The angle variables indicate where in the orbit you are, and provides a way of traversing this orbit. So what we do then is we basically put that into a sort of as a delta source in our Jacoby equation. Something that where the separability and the fact that Kerr has isolating integrals sort of influences this indirectly, in that there's a known sort of relationship between spacetimes that have these isolating integrals and the ability to separate wave equations and Schrödinger equations. So in many ways, I suspect that the very fact that we can write the Tucholsky equation in separable form is related to the fact that we are in fact working with spacetimes in which the isolating integrals exist. Finally, the implication, if you have a full set of isolating integrals or these action variables, is that the waveform that comes out is made up of 3 fundamental frequencies. There's a direct relationship between the frequencies, in fact, and the orbital elements. So what happens now if we're working in a space-time that is not Kerr? In fact, if you look at this waveform, can you determine whether it comes from, whether I've plagiarized it from Steve's website and I haven't cited him, or whether it comes from some other space-time, or in fact, whether it comes from nothing at all, where I've just hand-drawn the waveform so I don't have to cite anybody. So I guess, and also what happens to the orbits close to the spacetime? Can you in fact do this process in an arbitrary spacetime? Because if you can't, then it endangers to some extent our current Emery waveform sort of generation method. So let's have a look at, so Ilya and Jonathan from Cambridge have been looking at a number of spacetimes numerically. Oh, it doesn't want to do that.
So the fact that the full set of integrals gives separability.
So I'll get back to that later, but there's a relationship, there's a group that's been studying superintegrable systems, and there's a relationship between a manifold that has its geodesic, that has a full set of isolating integrals on the geodesics, and sort of wave functions like the Schrödinger equation and the wave equation that separate on it. But I'll come back to that in more detail. So let's look at a formulation for a whole bunch of compact objects that aren't bald. Basically, we now allow the possibility that we want to consider any space-time and check what our central object is like. And there's a very powerful statement in the exact solution sort of generation techniques, is that the set of current and mass multiple moments of any axisymmetric stationary asymptotically flat space-time uniquely identify that space-time. It was a conjecture made by Garrosh in the 1970s and later proved by the same people that made the HKX transformations which generate these space-times. So the idea that we will be considering space-times that have 2 commuting killing vectors on them for time and sort of azimuthal angle, and we'll be working in a vacuum. And all these space-times are then governed by Ernst's equation. It's a 4th order nonlinear differential equation that you solve, and then it determines all the metric functions. Okay, so now that we can have a way of uniquely labeling a space-time, we actually want to know what the signature is. How uniquely do the orbits determine the space-time? Because that's what we're going to be seeing. So, and the mathematical question is basically, can you find a full set of isolating integrals? And what is the implications for your observational signature and orbital confinement? So this becomes a problem in sort of a 2 degree of freedom problem in dynamical systems, which turns out to be reasonably thorny. Okay, so one of the space-times that Ilya and Jonathan have been looking at more carefully is the Manko-Novikov space-time. It is nice in that you can write down the closed form for a metric that's parameterized by all the mass multiple moments. So you have an analytic answer that models sort of an object with arbitrary mass multiple moments. You can, in addition, specify the spin, but you cannot as yet specify all the spin multiple moments. That hasn't yet been done. There's a proof that it can be done, but it hasn't yet been written down explicitly. These space-times have an event horizon. They have no curvature singularities outside of this event or killing horizon. And the only place where they have a bit of a problem is possibly on the equator, where they have a curvature singularity in some cases.
Is that really a curvature singularity? I mean, there's no horizon on this. There's a breaking horizon on the equator, but is that a singularity there?
The curvature scalars diverge. But this is not a serious problem. In fact, because it's just a line, you can still compute the area of these horizons, and they're parameterized by the multiple moments. So it sort of gives you a nice idea of exactly what's happening with the space-time. If the multiple moments AN disappear, you just have your ordinary Kerr and Schwarzschild horizon. So the reason that these spacetimes fail in O'Hare theorems is basically this problem. They have closed time-like curves very near the horizon. So this is an angular coordinate that changes along the horizon. The horizon is represented by this line, and you can see these blue regions are where you have these closed time-like curves. If you have a compact object that is actually larger than this horizon, then you have a valid space-time and you have a multiple moments asymptotically. If you now look at the ergo region, the spacetimes also have an ergo region. For comparison purposes, Kerr's ergo region looks something like this. You can see it corresponds with the event horizon at the poles and then bulges out beyond it. The quadrupole moment can, in the case of the Novikov spacetimes, kind of separates out these three regions as ergo regions. Now, to get to the question of whether we can actually describe the orbits, you start playing a lot of tricks with the geodesic equations. The first thing you do is you use the fact that you have two killing equations, or two killing, you have two killing vectors to eliminate the dependence of t and phi, and it allows you to reduce your Hamiltonian to something that's slightly less complicated. It takes out your two coordinates and your two conjugate momenta, and you're left with a four-dimensional phase space. You have a further restriction. You have the Hamiltonian constraint, which limits this four-dimensional phase space to a three-dimensional energy space. And the question you want is whether you have a fourth constant that you can use to describe your orbit. A typical example of the motion of this dynamic of these orbits is given by the effective potential that's determined by the Hamiltonian constraint. An example for Kerr is, it looks something like this. It determines the magnitude of your conjugate momenta vector. If you start in this region over there, you're going to have a bound orbit. If you start over there, you hit the back of the potential and go in, it's going to hit the singularity, which once again lies over there. So you have a very good description of what the orbits do. And in fact, to simplify the hunt for this constant,
What are the curves in that? Those are equipotential?
So these are equipotential sort of lines of V. Okay, so when V is equal to 0, there's no motion in your rho z plane. You're just going round in the phi and t direction. So that's just the top and the bottom of the equatorial plane. And it makes a nicer picture. So if I now, to be able to visualize the phase space, if I now were to slot this rho z plane, basically that thing, in at the bottom there, and have a look at my phase angle, which is related to p rho and pz in this fashion, then an orbit that is integrable will be tracing out a two-surface in this three-dimensional space. And this is one way of looking for it. A conventional way is to plot a Poincare map. And if you have a closed curve on this map, then you're sure you have a second invariant. If you don't, you definitely, you have proof that you don't have a second invariant. So let's now have a look at what Ilya and Jonathan see for the Novikov spacetime. They numerically integrated and they see something like this, which we don't understand. So they've looked at the Novikov spacetime. There's another group that's looked at Gouron little years. The sort of Gouron little years looked at another spacetime. They also see orbits that look reasonably chaotic. And you can recognize a chaotic orbit either by the Poincare slice or just by looking at it. If it looks a mess, it's a chaotic orbit. No, actually, you look for sort of crossing structures in your orbit. And if they're ordered everywhere, like at every point you have a certain number of lines leaving, and they remain the same for your whole orbit, it's a good indication that it's integrable. Whereas over here, if you look at every point, the number of lines that cross there vary. So that's just one more check. Now, in dynamical systems, generically, this constant of motion doesn't exist. If you take the group of all your dynamical systems and you throw a dart at them, you're not going to hit one that is integrable. There's another problem in dynamical systems. There's no complete test or algebraic test if you're given a Hamiltonian to test whether it's integrable or not. There are partial tests which are not completely understood yet. It is known that if the Hamiltonian passes this test, then it is integrable. There's no counterexamples. People don't fully understand why the test even works. The foolproof method that can disprove the existence of a constant is this numerical Poincare maps and the orbital invariance that I've tried to explain. And even if you suspect that you have a constant, there's no way of constructing it, right? And in our Emery problem, it's only useful if you can actually get the constant out. Why these difficulties arise, I'll try and explain in the next few slides. So the interesting thing is that, and something I've never seen in any sort of Hamiltonian or sort of Hamiltonian system I've looked at, is this region here. Outside, the orbits seem to be maintained to a very high degree of accuracy, which is unusual because usually if you don't have a constant for a Hamiltonian, you begin to fail in a systematic way, which we don't see with these spacetimes. So it is very difficult to put the two together and explain why you have chaos in the one and why you have such a lot of order in the other.
These are just different orders.
So, yeah, so this is basically the effective potential for this is the effective potential region in which your orbit is allowed. And in the Novikov spacetime, it's unique because it's split into two parts. So you have regions like this in Kerr, but you don't have regions like that in that correspond to this in sort of in Kerr. Yeah.
So those are the same. So those are different orbits with the same energy increment.
Yeah. Those just different initial conditions.
The same energy increment with different initial separation.
There's nothing qualitative that, other than that. I mean,
Yes.
no one goes into the ergosphere and the other does not.
This one does go into the ergosphere. So that one goes into the ergosphere, but it doesn't go into the closed time-like curved region. So that is an identifying feature. No, it does not go into the closed time-like curved region. The other thing that's different about this particular orbit is the effective potential at V is not convex. You have two lumps that stick out, whereas here it's basically just the amount that's been deformed. Okay, so the question now becomes whether these things exist or not. There's been a paper, a numerical or sort of analytic paper out that guesses the one. I mean, I guess you have two options. You guess they exist and you look for them, or you try and prove they don't exist. So there's a bit of confusion about exactly what to look for. One way of looking for a constant of motion is by means of the Hamiltonian Jacoby equations. What they do is you basically take your Hamiltonian, you plug in a function, you replace all your momenta with derivatives of a function j, and if you can solve this equation, it provides you with a transformation onto the orbits, onto the sort of the orbit itself. It generates a transformation that allows you to go from your global coordinate patch onto a coordinate patch that is ideally suited to your orbits. So a solution of this equation implies that you have a constant of motion. The one solution method is separation of variables, and it's the most common one used because then you can actually write down the answer. It's easy to write down the answer. And it was used by Carter when he first discovered the Hamiltonian, or the Carter constant for the Kerr spacetime. Now, no separation of this equation basically implies various things. It implies that, well, possibly you don't know how to separate the equation, possibly you are working in the wrong coordinate system because some of the equations are separable in one coordinate system but not in another. It could mean that the equation is in fact not separable. It could mean your equation is in fact not integrable, and most commonly it means you should look for another problem because you have a big problem here. But it doesn't mean that you don't have a constant of motion. And in fact, a counterexample is this guy. It's a Hamiltonian which does have a constant of motion. It can be written down explicitly. It's reasonably simple. It's cubic in P, but nobody's ever found a coordinate system in which it is separable. But this is not the only way of looking for constants of motion. In the last sort of 20 years in dynamical systems, there's been sort of a resurgence of interest and a much greater understanding of what you're actually looking for. But it is a very important historic method. Okay, so another space-time that I'm more fond of is the Zipway Fourier metric. Basically, is a one-parameter family of space-times that joins flat space to Schwarzschild. It has the interpretation asymptotically as being sort of having the multiple moments of a finite rod of dust. So I've looked at it sort of at various parameters, regions in the spacetime, and I haven't yet come across one that is chaotic, which is surprising. Usually, if you have a system in which an integral, if you don't have an integral, you usually hit at least one sort of orbit in which it's chaotic. If you look at it, if you scan the region finely enough. So when I made the suggestion that possibly a fourth order invariant does exist, it was for various reasons. One was this space-time that we see that you have this very clear structure. It is indicative of a fourth order invariant. And to see that, I guess one way of doing it is you basically guess the form of your invariant. You make a Fourier expansion of the invariant in terms of this phase angle. And if you then specialize to a particular point in your orbit, so you're basically fixing rho and z, you can then use this invariant and you can say, okay, say I put this thing equal to 0. There are only going to be 8 possible directions. Say, for example, I have n equals 4 in which this thing vanishes. If you further impose the fact that you're going to have to traverse the orbit in both directions, those 8 sort of collapse to 4, and it's a pretty clear indication that you're, so if you guess a fourth order invariant and you have a structure across, it implies that you're going to have a crossing structure like that. I guess the other reason is that if you do find it, it's amazingly useful because you have a way of parametrizing all the orbits in your actually symmetric space-time. You have a way of transforming onto these orbits and basically watching how, whether they move towards each other or move away from each other. If you imagine dust moving along these orbits, you can start looking for sort of more strong field effects of non-Kerr spacetimes. The other reason is that the Hamiltonians we're looking at are not generic. They have their origin in the Einstein field equations, which are known to be completely integrable. They pass the test that I mentioned earlier on. In fact, the very statement earlier on that you can uniquely identify your spacetime by its multiple moments comes from the fact that they are integrable and that there are solution generation techniques that take one of your spacetimes onto another one, etc., etc. So you can map any one of your spacetimes onto another spacetime. And the thing that interests me is what this implies for the geodesics. How do you have such a high degree of order in the actual spacetime mappings and lose it possibly for chaotic orbits? So the important thing, here are the field equations written down in my favorite form, which is the same way that the exact solution generation methods work. But the important thing to notice is that they have basically 6 generators. There are 6 functions in here that you use to describe it. Now, the relationship between curvature and your constant of motion is not understood in dynamical systems. I was actually quite surprised. It should be a natural sort of thing to look for. There just isn't any literature on it, mainly because the equations are so difficult to solve. Okay, so now let's go back. It's not entirely as hopeless as what I've let on. And look just at 2 manifolds, because eventually you can show that you can map that problem onto sort of a problem of looking for constants of motion in 2 manifolds. So the first constant, say you have a quadratic constant of motion, what does the 2 manifolds look like that, that have this? So back like in 1889, I guess, before people even conceived the idea that you could have chaos and you could possibly lose these constants, there was a mathematician named Koenigs that worked out the conditions on a 2 manifold that you could have them. And he basically got the following 3 results. He said, if you have a 2 manifold with more than 1 killing vector, it's a space of constant curvature. So if you look at the embedding diagrams of these spaces, it's basically you can have 0 curvature, you can have the sphere, which has positive curvature, or you can have your bugle, which has negative curvature. If you have any of those spaces, you know you have 3 killing vectors on your space, and you're fine. Now, if you want to check whether you have a second-rank killing tensor on, or second-order killing tensor on your space, you got the following results. If you have more than 3 of them, you know you're back to your first case. If you have 3 of them, you have a space of revolutions. So you can always integrate anything that looks as if it's been spun around its axis. And he identified 4 explicit types for these surfaces of revolution. And he interpreted the second invariant as being a Hamiltonian constant on a related metric, which was later rediscovered by Moser, who worked out the KAM theorem and has helped a little bit in understanding it. Anyway, his thing was lost, and there were people that were rediscovering this for the next 1,000 years. And in particular, the one I came across, because it's written in French, the one that I came across was a group, a Canadian group, that started working on super integral systems. And started exploring the relationship between the separation of the Hamilton-Jacoby equation and the wave equation and systems that have invariant on it. And in particular, they made the comment that 4th order killing tensors have 6 generators. So if you look for a space, yeah.
Sorry, I just had a question. Isn't the starting the second and third case just subcases of the first case? Because the first case is that any two manifold where the number of killing vectors is greater than 1, right?
Yes.
The regular greater than 3 and equal to 3 is a subset of that, right?
No. So if you have...
I'm sorry, I'm blind. Please forgive me. I just read tensors backwards. I apologize.
Okay, yeah. So I guess they broke down the conditions for a 4th order killing tensor on a 2 manifold. They said it has 6 generators, but they can't solve the equations, which is, so we have no idea what they look at. Now, even though we can write down what the conditions are on a manifold to have these things, we still can't check if a Hamiltonian does possess this property. The reason being is that you have a tremendous amount of coordinate freedom in sort of in your Hamiltonian. Your Hamiltonian can basically be an integral Hamiltonian that's been transformed in some other coordinate system. There are more than just coordinate freedom. There's a number of other transformations that maintain the fact that you have an invariant, but can disguise your Hamiltonian. So that's the basic problem. Okay, so there's a general theory that underlies the guesses that they had, or the previous results, that you can sort of use for basically guessing an arbitrary invariant, sort of an arbitrary order invariant, provided it's polynomial on your two-manifold. The method goes roughly like this. You eliminate your Hamiltonian constraint by introducing this phase angle. And what you are working with is a two-metric with your conformal factor V. You then go about and you say, fine, I guess my invariant, and I assume it's going to be polynomial in this, in the momentum. I basically make a Fourier expansion of the function that I have, where all these q's are now functions of rho and z. And then you go about computing the conditions on these q's for your guess to work. So you basically go d lambda dq d lambda is equal to 0. You do a lot of algebra, and you express your answer in terms of these complex functions. And the result you get is that you're looking for one unknown analytic function t, and then a series which corresponds to the coefficient, or is related to the coefficients of the highest order sort of mode in your Fourier expansion. And then you have a series, given that t, you have a series of recursion relationships which give you your lower order functions. The important thing to note, which simplifies later calculations, is that your even and odd terms decouple, and it allows you to limit a few things. The other important thing to note is the interpretation of this function t. In general, if you have an analytic function, it means it corresponds to a coordinate transformation that maintains the fact that you have this two-metric at the top. So it maintains your Hamiltonian structure if you make a coordinate transformation like that. So in the case to get a sort of geometric interpretation that is valid eventually for Kerr and Schwarzschild, you have the case that suppose you start with a two-metric and you have a killing tensor on it. For example, the example is this ellipsoid. You have an ellipsoid like this, you have your two-metric defined on it. If it is a function, if it is a two-manifold in which you can integrate the geodesic equations, then the Carter constant or the other additional constant corresponds to the Hamiltonian of a different two-metric that's considered conjugate to your other two-metric. So if you think about the interpretation of a killing tensor, it's basically a killing vector. It's basically a way of mapping your two-manifold onto itself without changing the geodesic structure. Your second-order invariant or your Carter constant is mapping the two-manifold that you're looking at onto another two-manifold, sort of basically mapping the geodesics of a two-manifold you're looking at onto another two-manifold. Now, what has this got to do with the Einstein equations? So the problem is in identifying whether your two-manifold has this killing tensor on it is basically a problem of coordinate freedom. You can't identify you don't know what coordinate transformation your two-manifold is. But in Einstein's equations, there's a trick in that you can connect you can find a way of connecting the coordinate freedom in your in Einstein's equations to the coordinate uncertainty in your killing equations, and it allows you to solve the killing equations reasonably easily. So all the integral systems we know in Einstein's equations are basically have the following properties. They are Petrov type D, so they have two null directions of the Wild tensor that coincide. They have a separable Hamilton-Jacoby equation. They have 4 separable metric functions, and they're characterized by 4 different families. And one of the families includes a family surrounding Kerr. The other family includes flat space, and there are 2 other families which I have no interpretation for whatsoever. How do you go about solving these problems, or this problem? You basically have your explicit expression for the constant, it's your killing tensor. You write down the killing equations, and if you cleverly split them, and this is also why the previous looking at the 2 manifold becomes relevant, you can get basically a killing equation for your 2 manifold part, just this component of the metric, and which is completely self-contained and decouples from the rest, and then you can get an expression for the other components of your killing tensor, which corresponds to sort of this part, which is slave to the components of this of the 2 manifolds you're looking at. So you need only consider sort of the conditions on the 2 manifold or the submanifold of this killing tensor. You can go on and you can process this part, and with a lot of algebra you can eventually show that this guy, or these equations basically imply that you're not looking for one 2 manifold that has a killing tensor on, but they actually provide you 3 more equations that have exactly the same structure. So you're actually looking for 4 2 manifolds that has a killing tensor on, and to which you can apply the previous sort of theory of sort of looking for sort of constructing your killing tensor. So, and in fact, you can explicitly find these guys or integrate them in terms of your metric components. So now let's just look at the conditions that your 2 manifold has a killing tensor on it. In fact, if you ask the question, how many 2 manifolds do you have which has a killing tensor on it, and how many of these contained in Einstein's equation, you get the answer that all possible 2 manifolds that have killing tensors on them have a solution in Einstein's equation, in Einstein's equations. So Einstein's field, or sort of possible Einstein spaces, includes all the 4 classes of 2 manifolds that were identified by Koenigs in 1889. The way to see this is the condition that you have a killing tensor on your 2 manifold basically comes down to, in some coordinate system that you don't know, your V has to obey the following 2nd order equation. And then from this side, or from these equations, it allows you to fix this analytic function, which in general you don't know, and you find that it is just quadratic in terms of your complex variable, which is just a combination of your rho and z. So you've basically you've solved the problem of having your coordinate freedom for the killing tensors by making use of Einstein's equations. The interesting interpretation is that the 4 families that were looked at by Carter basically correspond to the difference in the roots of these equations. So if you set these constants A2 and A1 to 0, you have flat space, you're making no coordinate transformation. If you set A1 is equal to 0, you have the set of spacetimes that correspond to Kerr's solution, and you basically have sort of 2 double roots, or 2 independent roots to that equation. And the other cases where you have 1 root or 2 roots that coincide correspond to the other 2 families of the spacetimes. But the important message there is that we contain all integral systems that have a 2nd order killing tensor on it, and it is the more restrictive condition on V. So let's now ask the question, suppose I have a higher order killing tensor on it, how much of that, or when does it happen that the conditions that you have a higher order killing tensor on your 2 manifold is less restrictive than the condition that your 2 manifold originates in Einstein's equations? Basically, that this V is related to the solution of Ernst's equation. And the point at which that happens is at order 4. So from the argument that you look at the crossing angles of the orbits, you don't have to consider order 3. It's excluded, it's not there. If you had a manifold that had an order 3 invariant on it, you would have 3 different directions at each point going out. Huh?
Which is sort of crazy.
Yeah, which is sort of crazy.
Well, it's conceivable, right? If along one of the crossings you always went in one direction, along the other crossing you could go in either that way or that way.
Yeah.
You could have an order 3 potentially, even with that crossing structure.
So actually, the example that I gave you where the Hamilton-Jacoby equation is not separable, but you still have an invariant, that will give, if you draw those geodesics, they look, I don't know. Anyway, they are order 3. They will have 3 directional crossing, 3 or 6 directional crossing sections, depending on which way, whether they traverse the geodesic backwards and forwards, or whether they're just going in one direction all the time.
So now, is that good or bad? What's the conclusion?
So the conclusion is, for Einstein's equations, you don't have to consider order 3, because the numerical simulations eliminate it, because of the cross-instruction of the geodesics. They also decouple. Order 3 and order 4 don't mix, which you can get from the earlier sort of analysis. Yeah.
I understand what you mean by the number of crossings. You showed the plots of the geodesics, the cross-section, theta, and C and whatever.
Right.
Do you mean the number of crossings, the number of directions? Like if you choose a point along the geodesic, or even in that like orbital force thing,
Right.
there will only be like 2 lines going through it.
Yeah.
Isn't it the case that if you let the orbit evolve for long enough, you just sort of fill in that whole orbital force?
Yeah, but I mean, if you still then blow up tremendously on that at a particular point, you're only going to have 2 crossings like this. So yeah, you're going to fill in the orbital torus, but if you then specialize to a particular point over there, you're only going to have a crossing like this. It's going to look filled in, but if you zoom up large enough, you eventually at each point are only going to have your 2 or your 4 possible momenta directions.
But can't you, can't you just let the thing run long enough that, I mean, if you say, oh,
You get to any given point from only 2 directions.
Yeah.
There'll be a point next to it that will have
Yeah.
quite a direction, but that very point.
If it's an integrable system.
If it's an integrable system. If it's not an integrable system, you're going to have that completely chaotic mess. Okay, so now order 4. It's the lowest order killing tensor that you have the condition that the killing equations are satisfied is not more restrictive than the condition that your potential comes from Einstein's equations. You can again do a whole bunch of work on it, and you can attempt to solve the 28 coupled killing equations for the 19 unknown components, which is a tremendous mess. If you choose your variables correctly, you can show that once again, just as in the previous case, you split the equations into at least 3 equations that have the same structure of looking for a 4th order invariant on a 2 manifold. Yeah, so that's what we can show at the moment. So in principle, once you're given that, you have the relationship between this T and your metric components, or the sort of the curvature. So you have the explicit coupling between your killing tensor components and your curvature. It is not yet pretty enough to be able to do anything with it. If you search the literature, there's no record of solution methods. There are exceptionally few examples of integrable systems that have order 4. They've just not been found. If you write down the equation that a 2 manifold has a 4th order invariant on it that looks like this, it's considerably more complicated than the 2nd order killing equations. And the question now that is interesting is that how large is the space of overlap between asking the question of how many 2 manifolds have this 4th order invariant, and how many and sort of whether they are a solution of Einstein's equations. The numerical evidence shows that you could possibly have a tremendous large overlap. And if this is so, and you can make the connection between it, you basically have a backdoor to the problem, because the solution generation techniques for these manifolds already exist. They are completely characterized, and they are known. So it'll be amazingly useful for dynamical systems people if this is so. Okay, now let's go one more step, and we say, what are the implications if an invariant exists for your waveform generation machine? Let's actually first ask the question, what happens if an invariant doesn't exist? So if an invariant doesn't exist, you lose the ability to uniquely characterize your orbit. It no longer looks nice and ordered like that. It is no longer confined to a fixed region. It will fill your sort of effective potential. So you have a rough estimate of where it is, but you don't know what it's doing. It's highly likely that putting it into your master equation, or even finding your master equation, is going to be very difficult because of the relationship between integrability and the sort of your geodesics and these type of wave equations. It generalizes to order 4. It's not entirely understood how this works. And finally, you're no longer going to have distinct frequencies, so your detection methods are going to be amazingly difficult. It's going to be difficult to pick out a waveform that originates from a fourth order, from a space-time that doesn't have integral orbits, from just random noise. And the other problem is, even if you get a waveform and you do the backward arrow, you're not entirely sort of assured that you have an interpretation of what is going on over here. Because the treatment out here is going to be perturbative. Whenever you're going to try and do a calculation, you're going to intrinsically assume that you have a constant of motion in order to do that calculation. So there is a lot of confusion. If, however, you have the result that you are uniquely characterizing your space-time, or an orbit can uniquely characterize your space-time, you have a powerful tool, because it most likely implies that the generalized wave equation for sort of translating your orbit from the strong field region into the asymptotic region can be solved. It's going to have the observational signature of sort of triperiodicity. The longer you watch it, the more accurately you can ascertain what action angle variables you have. The more accurately you can ascertain the orbit you are considering, and since you know that the orbit characterizes your space-time, the more accurately you'll be able to say or discern whether in fact you have a boson star, whether you have a space-time whose multiple structure differs with Kerr, and you should be able to sort of limit your sort of lack of knowledge of what these spacetimes are. You'll never be able to say with ultimate certainty that you have a spacetime with a certain multiple structure. All you can do is make a quantified statement as to what class of spacetimes could possibly result in a particular waveform. Okay, so I guess the conclusions basically are, if you have a fourth order invariant, you have a reasonably powerful observational tool for the Emery problem. It provides in some way an unambiguous interpretation of your asymptotic waveform. It could bring a certain amount of rigor to your discerning of what spacetimes you actually have. And a template bank based on sort of a number of waveforms that characterize all the stationary asymptotically flat sort of spacetimes would be a lot more robust than Kerr to small deviations in your waveform, and may increase your chances of detection. Now, we don't have it yet, and that's an important thing to remember. It's nonetheless, the numerical evidence shows that it's very likely that a large class of spacetimes have these invariants, And an understanding of it will further, and the relationship between curvature of the curvature of the spacetime and this invariant would be a result that basically pushes the bounds of mathematics and physics beyond the present day frontiers. Thank you very much.